Hello and welcome back to the podcast, everyone. Episode 141. Mark, it feels like the tech world has been especially busy lately, doesn't it? More than usual, maybe?
Oh, definitely, Jenny. It's like trying to drink from a fire hose sometimes, but, in the best way possible, right? There's just so much happening. And speaking of fire hoses, NVIDIA's GTC keynote back in March. Wow. I'm still sort of processing some of that.
Right? Jensen Huang on stage pulling rabbits out of a hat? Or maybe GPUs out of an oven? I saw the headlines, but I knew you'd have the real deep dive. Honestly, where do we even begin?
Okay, deep breath. Let's start with the star of the show, the main event, the new Blackwell GPUs. The big news is, they're actually in production now, shipping later this year, which is, well, it's significant.
Blackwell. Yeah, I remember the buzz around the name. But what makes it such a big leap compared to, say, the previous generation, Hopper? Is it just faster, or is there more to it?
Oh, it's asterisk way more than just faster. Calling it special is underselling it. Depending on the task, particularly inference on large language models, we're talking about a performance increase of potentially 20, 30, even up to 40 times over Hopper, under specific conditions. 40 times, Jenny. It's a serious jump.
Okay, hang on, Mark. 40 times? That sounds almost difficult to grasp. How are they achieving that? What's the secret sauce? Is it just cramming more transistors in?
Less secret sauce. More incredible, painstaking engineering. A big part of it is a new chiplet design. Imagine instead of one giant, monolithic chip, they're using two very large compute dies, perfectly stitched together to act as a single, unified, incredibly powerful processor. It's like building a V12 engine by combining two V6s, but making it work seamlessly.
Ah, okay. Chiplets. I've heard that term. So, smaller pieces working together as one giant brain?
Exactly. And then there are the interconnects, how these chips talk to each other and to other GPUs. They've got their new 5th generation NVLink, which provides something like 1.8 terabytes per second of bandwidth between asterisk GPUs. Think of it not just as superhighways for data, but maybe like dedicated bullet train lines connecting different parts of a massive city.
Bullet trains for data. I like that visual. So, beyond the impressive numbers, what does this 40x potential actually at times enable? Is it just about making current AI tasks faster, or does it unlock fundamentally new possibilities?
It's definitely both. But the new possibilities part is really exciting. This kind of horsepower unlocks the practical ability to train and run AI models with trillions of parameters. We're solidly moving into the exaflop scale computing era for AI. Think about extremely complex scientific simulations, modeling climate change with much higher fidelity, discovering new drug candidates by simulating intricate molecular interactions at scale. Jensen even made this poetic comment: tokens decode laws of physics. It's about using AI to understand the fundamental workings of the world in ways we couldn't before.
Trillion parameter models. Decoding physics. Okay, that puts it in perspective. It's not just an incremental step up, like going from a 4K TV to an 8K TV. It's more like going from radio to television, enabling entirely different kinds of computation and understanding.
That's a great analogy. And this power surge ties directly into another major theme from the keynote. This concept Jensen kept emphasizing: AI factories.
AI factories. That sounds very industrial. Is it essentially just a fancy, rebranded term for a data center, Mark? Or is there more substance to it?
It's yes and no. It's more than asterisk just times rebranding. Huang's argument is that we're seeing a fundamental shift. Traditional data centers were primarily built to store and manage information, maybe run some business applications. These AI factories, though, are purpose-built facilities designed specifically for asterisk generating times intelligence at an industrial scale. Think highly optimized environments purely for training and running these massive AI models, churning out insights, predictions, creative content, scientific discoveries. Whatever the AI is designed for.
Okay, so less about storage, more about processing and creating. Like a traditional factory takes raw materials and produces goods, these take data as the raw material and produce intelligence or tokens, as you mentioned.
Precisely. You feed them curated data, computational instructions, and they output, well, tokens, which can represent language, code, chemical structures, biological sequences, commands for a robot, physics, simulations, you name it. NVIDIA sees this as a major transformation in the economic value chain of computing infrastructure. Some analysts they cited are pointing towards a potential $1 trillion expansion just for this kind of reasoning and AI factory infrastructure.
$1 trillion. Wow. These numbers are consistently huge. So the expectation is that companies will start building these dedicated AI factories, or perhaps renting capacity in them?
Both, most likely. The idea is that generating AI insights becomes a core industrial process, similar to how manufacturing operates today, and it requires specialized gear, not just the Blackwell GPUs, but also super-fast networking like their new quantum InfiniBand switches and Spectrum-X Ethernet, the sophisticated cooling systems. The whole facility is designed as a single, integrated system for this specific purpose. It's a different beast than your typical cloud server farm.
It makes sense when you talk about needing that kind of environment for those trillion-parameter models. But, Mark, building and running these massive facilities, it must raise questions about the environmental footprint, right? All that power consumption?
That's a really important point, Jenny, and something that's getting more attention. Building more powerful chips in larger data centers, or AI factories, inevitably means higher energy demands. While NVIDIA talks about Blackwell being more energy efficient, times per flop, compared to Hopper, the sheer scale of deployment means the total times energy consumption for the AI sector is going to grow substantially. Critics are right to push for more transparency and investment in sustainable energy sources and more efficient cooling technologies for these facilities. It's a challenge the whole industry needs to tackle head-on.
Yeah, it's a necessary conversation alongside all the excitement. Okay, so AI factories churning out digital intelligence. But Jensen also pushed beyond that, didn't he? Something about a huge opportunity in physical AI?
Oh yeah, and this is where things get really interesting, potentially even a bit sci-fi, though the near-term applications are very practical. He talked about a potential $50 trillion total addressable market in heavy industry being revolutionized by physical AI. This umbrella term covers robotics, autonomous systems, and importantly, digital twins.
50 trillion? Okay, seriously, where do these numbers come from? It's almost too big to comprehend. What does physical AI mean in practice? Are we finally getting those robot butlers? Or is it more grounded?
Maybe eventually on the butlers. But think more practical for now. Imagine highly intelligent, adaptable robots in complex manufacturing environments, working alongside humans. Think logistics centers and warehouses run almost entirely by autonomous systems. And then there are digital twins. These are highly detailed, physically accurate, real-time simulations of physical objects, processes, or even entire systems. Using the power of platforms like Blackwell, you could simulate an entire factory floor, or a city's traffic flow, or the aerodynamics of a new aircraft design.
Okay. Digital twins. So you create a virtual replica of something real. How does that connect back to the physical world then?
That's where it gets powerful. You can test changes, optimize processes, train AI agents, or predict failures within the simulation, which is much faster, cheaper, and safer than doing it in the real world. Then, you apply those learnings or optimized parameters back to the physical system. For robotics, they talked about their Project GR00T's foundation model for humanoid robots and a new computer, Jetson Thor, designed specifically for them. They're using Isaac Sim and Omniverse platforms to create these realistic simulations for training.
So using the simulation power to interact with, optimize, or even times things for the physical world. That connects the dots. They mentioned something called physical sim to real pipelines?
Yep. That's the core concept for training robots or autonomous systems. You train the AI extensively in a high-fidelity simulation, letting it learn through millions of virtual trials and errors, and then transfer that learned intelligence, that brain, to the physical robot operating in the real world. Blackwell's sheer simulation capability is what makes creating these ultra-realistic virtual training grounds feasible.
That's clever. Train it virtually, deploy it physically, reduce the real-world bumps and bruises, I guess. Now shifting gears slightly, but still on the theme of enabling things. They also open source something called cuOpt, right? What's that about?
Right. cuOpt It's a software platform specifically designed for decision optimization. Think really complex logistical problems. The classic traveling salesman problem, but on a massive scale. Things like figuring out the most efficient routes for thousands of delivery vehicles in real time, or optimizing complex supply chains with shifting variables, or scheduling intricate factory operations. These are computationally intense problems.
Okay, so high-level problem solving for businesses. Why open source it? Isn't that giving away valuable tech?
It's a strategic move. By open sourcing cuOpt, NVIDIA makes these powerful optimization tools accessible to a much wider range of companies, researchers, and developers who might not have afforded a proprietary solution. It fosters an ecosystem, encourages people to build on top of it, and crucially, it demonstrates the practical value of their hardware. Because running these complex optimization algorithms efficiently still often requires powerful GPUs. It helps drive adoption and showcases the platform's capabilities for solving tangible business challenges. Democratizing access can spur a lot of innovation in logistics, operations, research, and beyond.
That makes sense. It's not just about selling the hardware, it's about building the community and the use cases around it. Okay, so we have Blackwell providing immense power, AI factories churning out intelligence, a huge push into physical AI and robotics, and tools like cuOpt becoming open source. That's a packed agenda. Did Jensen give any hints about what comes times after times Blackwell? Or are they taking a breather?
A breather? Not in Jensen Huang's vocabulary, apparently. This was another key strategic point he hammered home. He explicitly stated, NVIDIA is moving to an annual cadence for their major infrastructure platforms. They plan to release significant upgrades, new GPUs, new switches, new systems, every single year.
Every year? Wow. That pace feels relentless. Is that sustainable, both for NVIDIA and for their customers who have to integrate this stuff?
It's definitely ambitious, and it raises fair questions. Huang positioned it as providing predictability for customers. They know a new generation is coming each year, allowing them to plan their infrastructure roadmaps and investments accordingly. On the flip side, as some critics point out, this rapid cycle could pressure companies into costly upgrades more frequently than they might like, potentially leading to faster hardware obsolescence and e-waste concerns. It's a trade-off.
Yeah, I can see both sides. Predictability is good, but constant upgrade pressure can be tough, especially for smaller organizations. Maybe that's something we could ask our listeners. How does that annual cadence feel from their perspective? Is it exciting or daunting? We could put up a poll on the show page.
That's a great idea, Jenny, because it also keeps the intense pressure on competitors like AMD and Intel. NVIDIA isn't resting on its laurels. They're actively accelerating. Huang even pre-announced the times architecture after Blackwell, codenamed Rubin, expected around 2026. With Rubin Ultra following in 2027, they're signaling their roadmap years in advance.
It certainly sends a clear message. Keep up or get left behind. You mentioned competitors, but even big players seem reliant. I remember seeing that quote from Yann LeCun at Meta basically saying, "Keep the chips coming, we'll take all you can make."
Pretty much sums it up. LeCun's full quote was something like, "We'll need every flop NVIDIA can produce." Maybe even hinting they'd need asterisk more times than NVIDIA can produce. Even companies like Meta, Google, Amazon, who are developing their own custom AI silicon, still buy enormous amounts of NVIDIA GPUs. The demand for AI compute is just voracious right now. There's not enough to go around.
Which brings up another point some people raise. The potential risks of relying so heavily on a single dominant supplier for such critical infrastructure. Is that a healthy situation for the market?
That's the classic market dynamics question, isn't it? NVIDIA has earned its current position through strong execution and innovation, but significant dependence on one company always carries risks. Potential pricing power, supply chain vulnerability if something disrupts their production, maybe even a slower pace of innovation in certain areas if competitive pressure lessens. Encouraging a diverse ecosystem with multiple strong players is generally seen as healthier long-term. But right now, NVIDIA is just leading the pack by a significant margin in high-end AI training hardware.
So wrapping this GTC whirlwind up, the big picture seems to be, NVIDIA is building exponentially more powerful tools like Blackwell, creating specialized AI factories to deploy them at scale, pushing hard into simulating and interacting with the physical world through robotics and digital twins, and driving this all forward on a relentless annual upgrade cycle, even while providing ecosystem tools like cuOpt.
That's a perfect summary, Jenny. It's a bold, integrated vision for the future of computing, shifting the focus from just processing information to actively times generating times intelligence as a core industrial output, and embedding that intelligence everywhere, from massive data centers right down to individual robots.
It's certainly a lot to digest. The immense opportunities, the scale, the speed, and those valid concerns about sustainability and market concentration. Makes you wonder what next year's GTC will bring if times is the pace they're setting now.
Right? We'll probably need a whole new set of vocabulary by then. But it's undeniably an exciting and pivotal time to be watching this space.
Indeed it is. Well, Mark, thanks for navigating us through that storm of announcements. My brain feels considerably fuller, maybe stretched a little thin in places, but definitely informed.
Hey, happy to help stretch it. Always fun diving into this stuff, Jenny. And don't forget to check out that poll on the annual Cadence, folks.
Will do. All right, everyone. That's all for episode 141. Join us next time for more tech explorations. Bye for now.
See ya.